Okay, we return to our seminar. I see some new participants, so welcome to everybody to our seminar. I hope you had some rest from between these talks. For me, for instance, it was sufficient time to run to the ocean and take a bath. So it's a pleasure for me to present Professor Pavel Kolesnikov from Novosibirsk, and he will speak on derived algebras and their identities. Pavel, are you ready?
Yes, thank you very much for the invitation to submit a talk at the conference. I can't see myself. Can you see myself in the system or just presentation?
Yes, it's okay.
Oh, sorry. Good. This is a very wonderful opportunity to submit a talk at a seminar, regular seminar in Brazil, you know. I've just noticed that the number of participants, regular participants of the seminar, is approximately the same as on a conference. So practically you have a weekly conference in algebra and related topics. The topic of derived algebras is a very simple one. Actually, I'll try to explain how to understand the definitions and how to calculate things. Let me first start with notations. I will use the following notations for classes of associative and non-associative algebras. Not necessarily with one operation. I will also mention Poisson algebras with two operations, but mainly the algebras are with binary operations. As I will use for associative algebras, com for associative and commutative. So just commutative means not only commutativity but associativity as well. Lie algebras, Poisson algebras. The varieties algebras will be denoted in this way, and I will also use the same notation for operads corresponding to these classes of algebras. I will later explain what is an operad quite briefly. Another class which is less known but crucially important for my today's talk is the class of Novikov algebras. There is a very simple thing. If you consider a commutative algebra with a derivation is just a linear map which satisfies the well-known identity since the basic calculus course. Given such an algebra, one may define a new operation on the same space A, as was for initial commutative algebra. A circle B would be just the product of A and B prime, the derivative of B. Then it's quite easy to check in a straightforward way that the following relations hold. So-called left symmetry, and right commutativity. Here you may say just the associator of A, B, and C, and here the same associator with permuted A and B. Such an identity is called left symmetry, and this one is right commutativity. The operators of right multiplication commute. These identities emerged in a paper by Gelfand and Dorfman with relation to formal calculus of variations. And also, Balinsky and Novikov introduced these algebras related to linear Poisson brackets, related to a problem of classification of linear Poisson brackets. And it is essential to note that apart from left symmetry and right commutativity, there are no other independent identities that hold for the operation circle. It follows from a paper by Jumadildaev and Lofal of 2002. They proved that the free Novikov algebra embeds into free differential commutative algebra. And therefore, if an identity holds for commutative differential algebra, then the same identity must be true in the free Novikov algebra. But, well, Novikov, I mean, generated by these two identities. So there are no other independent identities. A little bit stronger result was recently proved by Bokut, Chen, and Zhang. Hi, Zerui. They proved that every Novikov algebra may be embedded into a differential commutative algebra. There exists a sort of differential envelope for every Novikov algebra. I also have to consider another class of algebras, which emerged in the same paper by Gelfand-Dorfman of 1979. This class of algebras is known as, in the literature, as Gelfand-Dorfman bi-algebras. But in order to avoid a collision with the notion of a bi-algebra as, you know, an algebra with coproduct, I will use the term Gelfand-Dorfman algebra, or GD algebra for short. These algebras have two binary operations, circle and bracket. Bracket is a Lie, satisfies the identities of Lie algebras. Circle is a Novikov algebra. And there is a single relation which defines the interaction between bracket and circle. This strange-looking identity is given here. And in particular, every Novikov algebra, consider it as a Lie algebra relative to the commutator. The commutator on a Novikov algebra is a Lie one. This is well known. It's left-symmetric, means Lie admissible. This commutator actually satisfies this strange-looking identity. So every Novikov algebra is actually a GD algebra. This class of algebras was also related with the formal calculus of variations. It was noted by Xiaopin Su, probably the first time, that a Poisson algebra, ordinary Poisson algebra, equipped with a derivation. The derivation is supposed to be a derivation relative to both operations. It satisfies the Leibniz identity both for commutative multiplication and for Poisson bracket. Every Poisson algebra is in particular a Lie algebra, of course, relative to the bracket. The circle operation, defined as before, turns a Poisson algebra into a GD algebra. And this slide actually presents a problem which was a trigger for me somehow to study the main topic of my today's talk. I will not discuss this problem, but this problem here was a trigger for me to study the problem, the entire problem. What about other identities that hold for circle and bracket on a differential Poisson algebra? Are there any other identities that do not follow, that are not consequences of GD algebras identity? And the answer was positive, actually. Some of such identities were found in my paper with Baurjon Sartayev and Aybola Razgaliev, recently published. So in this case, such identities exist. And now Baurjon is about to find the complete list of such identities. But that problem presented here was just a reason to consider the following very simple question. Suppose we have a non-associative in general algebra. Well, non-associative. Well, this associative is not supposed to be here, so I had to write non-associative. So this algebra A is non-associative in general, but it might be associative as well. Equipped with a linear operator, doesn't matter which one. We may define new operations. Let us define them left product and right product. The left product is defined in this way. Dot is the initial operation, and right product is defined in this way. Let us denote a system obtained on a space A relative to these two operations as AT. And we may also leave the initial multiplication in the language and consider a system with three binary operations, left, right, and the initial one. Let us denote the system by AT star. Now, what can we say about, suppose we know that the algebra A belongs to a variety var, say associative, Lie, commutative, and so on. What can we say about the identities that hold on these derived algebras, AT and AT star? Of course, we have to state the question as follows. What are the identities that hold for all such algebras when A ranges through the entire variety var and T ranges through not necessarily the entire end A, but maybe some class of operators? A kind of toy example, very simple one, appears when we consider associative algebras, and arbitrary operators T. In fact, it's not hard to show that the only identity that actually holds on such a system, AT, is the so-called L identity, or central associativity in some sense. It is very easy to show that this identity actually holds, but actually there are no other identities that hold for such operations in the case when T is an arbitrary operator and A is an arbitrary associative algebra. But a little bit more interesting problem. What if we fix a variety of algebras with binary operations? Here I consider only one binary operation, but we may consider several binary operations as well. There will be double family of operations on AT. What if we restrict the class of operators? What if we suppose the class of systems A sub T, where A ranges through the entire variety var, and T belongs to some particular class of operators. So the entire variety of ATs will be smaller, and we may expect more identities. There is a question. This question has an answer in a very famous case, namely, historically, it turns out historically that the very natural class of operators called Rota Baxter operators. If we restrict the family of operators to Rota Baxter operators, then there is an answer. Let me recall the known results. Suppose we have an algebra in a variety var, say associative, Lie, commutative, Poisson, and so on, and a linear operator T, which satisfies the following identity. This identity defines so-called Rota Baxter operators, a very popular topic, mainly in mathematical physics. And one may actually see that this relation of Rota Baxter operator of weight 0 is a formal presentation of the integration by parts. Rota Baxter operators of weight 0, they provide us a formalization of the integration operator. Then the algebra A sub t, obtained as before, belongs to a class so-called pre-Var algebras, those obtained by so-called dendriform 2-split of Var. This dendriform 2-split is a canonical procedure. I would like to avoid explaining in details, but this is a very simple procedure actually. So we may produce the identities of pre-Var from identities of Var in a canonical way. The same thing happens if we consider Rota Baxter operators of non-zero weight. Of course, up to some scaling, it's sufficient to consider weight 1. Rota Baxter operators of weight 1 are defined by this identity. And if we have an algebra in a variety var equipped with a Rota Baxter operator of weight 1, then AT star would belong to so-called post-Var algebra class, which is obtained by dendriform 3-split of Var. These pre-Var and post-Var, they also called successors of Var. Well, but this result gives us one-side implication. If we have an algebra from Var with operator or Rota Baxter operator, then what we obtain would be pre-Var or post-Var algebra. The converse is also true actually, but I'll say a little bit later. Some examples of dendriform split are also well known, very well known. For example, the dendriform 2-split of Lie algebras is exactly the variety of left-symmetric algebras or pre-Lie algebras. Of course, pre-Lie algebras, they have only one operation instead of dendriform 2-split, which has two operations. But when we deal with anti-commutative algebras, then we can replace two operations by one, assuming anti-commutativity. The dendriform 2-split of anti-commutativity is given by this particular identity. So we may express everything in terms of only one operation. And in terms of this particular operation, what we obtain would be left symmetry. If we replace everything with not right but left multiplication, then we obtain right symmetry, of course. Another well-known example, the dendriform split of commutative algebras. Pre-commutative algebras, this is exactly the variety of Zinbiel algebras. Non-associative algebras defined by this particular identity. Again, the dendriform 2-split allows us to express everything in terms of only one operation. In terms of this operation, what we obtain would be exactly the Zinbiel identity. Sometimes in differential geometry, this identity is called half shuffle algebra identity. Zinbiel algebras were invented somehow in differential geometry under the name of half shuffle algebras. One more example of dendriform splitting was also proposed by Ladey. When we deal with, associative algebras are supposed to be here. If we apply the dendriform splitting to not commutative but associative algebras, then what we obtain, the variety of pre-associative algebras, is exactly what is known as dendriform algebras. Pre-Poisson algebras were also well known from the paper by Aguirre. And there are many other splitted identities under consideration, say pre-Jordan algebras and so on. So in general, what we have, given a variety Var, an algebra from Var, a Rota Baxter operator, let us consider only the case of weight 0 for simplicity. Then the corresponding algebra A sub t would be a pre-Var algebra. What about the converse? Can we say there are some identities that hold on such A sub t that do not follow from the defining identities of dendriform split? The answer is no, actually. It is possible to show that every pre-Var algebra, or post-Var, in fact, can be embedded into an envelope, into a Rota Baxter envelope. For pre-Var algebras, the envelope is with Rota Baxter operator of weight 0. For post-Var algebras, we can find an envelope with Rota Baxter operator of non-zero weight, or say weight 1. So this embedding actually shows that the answer to that question is no. There are no other identities, so the dendriform 2-split or 3-split is exactly the class of algebras like AT, the variety generated by all algebras of this form. In this particular case, as we may say, the answer to the initial question is well known. Another case when the answer is known in the literature is the class of so-called averaging operators. And the answer is somehow dual to the definition of averaging operator is dual to the definition of a Rota Baxter operator. And the question is actually the same. There are no other identities apart from those obtained by so-called replication procedure. The procedure was described in my paper many years ago, but the title, the name of the procedure was proposed by Pei, Bai, Gu, and Ni. So I use the term for the procedure from their paper, recent paper. An example of replication is also well known. The replication of Lie algebras is exactly the variety of Leibniz algebras, often considered as non-anti-commutative analogs of Lie algebras. Again, the replication has two operations, but in the Lie case, we may replace them just with a single one. So we have two cases when the answer is known, Rota Baxter operators and averaging operators. But as you may remember, Rota Baxter operators, they present integration. They present a formalization for integration. What if we replace the integration with a derivation? This is a very natural thing, actually, because derivation is also a very important thing in algebra. So suppose we consider a variety of algebras with binary operations and a derivation, all possible derivations of these algebras. What can we say about identities that globally hold on all derived algebras? With two operations, left and right, or even with three operations, left, right, and the initial one. Let me formally state a definition of a derived identity, however, it's more or less clear. Suppose we consider a variety of algebras with only one, for simplicity, just for simplicity, but it is essential that the operation is binary. A non-associative polynomial, a polynomial in two operations, left and right. So this is a linear combination of formal terms in formal variables x1, xn with two operations, left and right, we would say this polynomial is a derived identity on the variety var if every system of the type A sub t obtained from an arbitrary algebra A in var and with arbitrary derivation t of that algebra A satisfies the identity f equals 0. So for every f x from A, the value of the polynomial would be 0 on A. And the general derived identity is just the same, but polynomial with three operations. That polynomial f would have three different operations. And then we would say general derived identity is a polynomial which gives us an identity on AT star for all possible A's and for all possible derivations of A. This is exactly what I was saying before. And the main problem of my talk, the topic of my talk, is to say how to find that derived identities and general derived identities. The solution is not very hard, but curious in some sense. So the main topic is how to find the derived identities and general derived identities. There are two examples when the list of derived identities is well known. One is related to commutative algebras, when var is commutative. In this case, as I mentioned before, the derived identity dcom is exactly, well, I'm saying isomorphic because we have to consider this variety as a variety of algebras with single operations. So the categories are equivalent in some sense, in the natural sense. So the derived identity of commutative algebras is Novikov algebras. And the general derived variety d star com is equivalent to the variety of so-called differential Novikov-Poisson algebras. Also considered in a paper by Boku, Chen, and Zhang, a different paper, however. D star com is a variety of algebras with two operations. Say ast and star. One operation is associative and commutative. Another operation is right Novikov. Well, of course, we may rewrite everything in ordinary Novikov form. So right Novikov means right symmetric and left commutative. It's opposite to Novikov algebras. And there are two identities that are responsible for interaction between them. Differential Novikov-Poisson algebras can be embedded actually, well, every differential Novikov-Poisson algebra can be embedded into an ordinary commutative algebra with a derivation. In the paper by Boku, Chen, and Zhang, it was shown. So we may say that in this case, there are no other identities apart from these ones. But in order to answer the question in general, how to deal with an arbitrary variety, we have to use the language of operads. Let me very briefly explain in a sketched form, explain what is an operad and what can we do to them. The term operad comes from operation and monad. Every operad is actually a category. Operad is a category with a single object. This is why it is called a monad. The object is unique, but the category structure is richer than the structure of an ordinary category. instead of a single morphism set, we have a family of so-called multi-morphisms. We will consider linear version. So in a linear version, all these sets, the sets of multi-morphisms, corresponding to an arbitrary natural number, they are all linear spaces. By the way, the characteristic of the ground field is supposed to be 0. I forgot to say about that. From the very beginning, the characteristic of the ground field is 0. Every family, every space from the family is a module over the symmetric group. And there is a composition rule. We may compose a multimorphism of degree n with the multimorphisms of degree, say, m1, so on, m2, mn. And the result would be a multimorphism of degree m1 plus m2 and so on plus mn. So instead of a single morphism space, we have a family of morphism spaces. And the composition is more complicated than in the case of ordinary category. But other axioms are actually the same. This composition must be associative in a very natural sense. There should be an identity morphism from the first space. And the composition mentioned here must be equivariant relative to the symmetric group action. So this equivariance means if we act by some permutation to all components of the composition, then the result would be the same as the initial composition under the action of some natural composition of permutations. The most natural example of an operad is an operad related to a particular linear space. If we fix a space and denote the space Vn, that will be a sort of single object of an operad. The set of multimorphism would be just the space of multilinear maps from V to V, multilinear maps of RETN. The composition is very natural. A symmetric group action is just permutation of arguments. All the axioms hold, so we obtain an operad. For us, in order to apply to algebraic problems, another class of operads will be essential. Operads related to varieties of algebras. Suppose we have a variety of algebras, not necessarily binary, by the way. We may consider the free algebra of the same language. In the case of associative algebras, for example, the free algebra would be the magmatic algebra. All non-associative polynomials. Let us consider multilinear polynomials of degree n, exactly in the variables x1, xn. So every polynomial from mn of x would depend exactly on x1, xn, degree 1 by each variable. And let us consider the quotient of the corresponding space, the quotient by the intersection of the magmatic space with the ideal of identities defining the variety var. This space var n is exactly the same space as used for calculating codimensions of a variety. This is exactly the same stuff. And we may consider the family of spaces like that as an operad, relative to a very natural composition. In order to compose monomials from this space, I consider monomials from Mn, of course, but assuming they are images in the quotient. The composition is defined by substitution and renumeration. Let me simply show on an example how to compose a 3 morphism like that with 2 morphism, identity, and another two morphism. In order to calculate such a composition, we have to substitute the first one for x1, the second one for x2, and apply renumeration. So x1, x2 are busy, so the next one would be x3. And this blue guy goes for x3, also with renumeration. So the result is supposed to be here. Very easy to calculate and natural. And the main stuff is that given a space V, in order to define an algebra structure on this space V, we have to define a morphism of operads. Morphism of operads is just a component-wise family of linear maps from var n to vn. So every term from var n gives rise to a multilinear function on V in a very natural sense. In order to define an algebra structure in such a way that the algebra obtained belongs to a variety var, we have to define a morphism of operads like that. And there are many algebraic constructions that can be explained in terms of operations with operads. We will need so-called Manin products of operads and also Koszul duality of operads. Let me again very briefly and in a sketched form explain what are these two guys, Manin products and Koszul duality. As you definitely know, an arbitrary algebra may be, say, in a variety var, may be defined by generators and relations. The basic thing in algebra. In a very same way, an arbitrary operad may be defined by a space of generating operations. Let me denote it simply by V. This is a graded space because the operad, as you may, an operad is a collection of spaces. So the generators would form a graded space, Z plus graded space. This is a symmetric module, of course. Instead of generators, we have a graded space of generating operations, symmetric module of generating operations. Starting from an arbitrary space like that, one may define what is called a free operad generated by V. The elements of free operad, the elements of spaces, they are obtained by all possible compositions, of operations from V. And in order to get a quotient, we need a space of defining identities. This is a graded subspace, of course, a graded subspace in the free operad. And then, given such graded subspace of defining identities, one may uniquely determine an operad generated by V with defining relations R. We say the operad is binary if the generating operations are all concentrated in the second component of the graded space. So all operations are binary, in other words. And an operad is said to be quadratic if the defining relations, all defining relations are concentrated in the third component of the free operad. That is, defining identities are of degree 3. Of course, say commutativity or anti-commutativity, they are of degree 2. But commutativity and anti-commutativity, they are written in the symmetric module structure. So we are considering this V2 as a space of, say, two operations, x1, x2, and x2, x1. In this case, all algebras like associative, alternative, Lie, Poisson, Novikov, and Gelfand-Dorfman algebras, they are all quadratic. The defining relations are of degree 3. Suppose we have two operads, binary quadratic operads given in this way. The operation of Koszul duality and Manin products for operads were proposed by Ginzburg and Kapranov. They act as follows. In order to get the Koszul dual operad, we have to get dual space. It is actually transpose dual. The symmetric group action is the action has the sign of parity. Odd permutations add negative sign here, but this is not very essential. And for the defining identities, we have to get the orthogonal complement of the initial one. So if O was defined in this way, the Koszul dual is defined in this way. The Manin white product is generated by the tensor product of the generating spaces, and the defining relations are obtained in this way. Also, there is a Manin black product, also generated by the tensor product of V1 and V2, but the defining relations are given in this way. Sorry, it seems like they should be. Yes, definitely. They should be, sorry, R1 tensor R2, actually. The formula here is a little bit wrong because the duality holds. The following duality holds. Koszul dual to the white product is black product of duals. In order to get this one, I was copy paste. This is a copy paste error actually. Sorry. So here should be R1 tensor R2. For example, if we consider the Gelfand-Dorfman algebras, then the Koszul dual to Gelfand-Dorfman algebras would be exactly the variety, the operad corresponding to the variety of differential Novikov-Poisson algebras mentioned above. The dendriform splitting may be described with Manin black product. It was found by Bruno Valette that in order to get pre-Var algebra, we have to consider the Manin black product of pre-Lie and Var, where pre-Lie is the dendriform splitting of Lie, left-symmetric algebras. The replication procedure can also be described in terms of Manin white product. In order to get the replication of Var, two replication of Var, we have to consider the Manin white product of Var, the operad corresponding to Var, with the operad of perm algebras. Perm algebras, I haven't written here what they are, associative and left-commutative. Perm algebras are associative and left-commutative. However, the white product is easy to define for arbitrary binary operads, not necessarily quadratic. Given two operads, O1 and O2, suppose they are binary. One may define so-called Adamar product of operads. The corresponding families are just tensor products of the families of operations of these two operads, and the composition is component-wise. So we have to consider composition here and composition here quite naturally. The symmetric group acts also in a component-wise way here and here. The resulting operad is not necessarily even binary, actually. But if we consider the sub-operad generated by all binary operations, this sub-operad is exactly the Manin white product in the case of quadratic operads. But one may easily use the same construction as a definition of what is a Manin white product in not necessarily quadratic case. And the main theorem I would like to present is exactly here. It turns out that if we consider a variety var corresponding to an arbitrary binary operad, so the variety with binary operations and no other restrictions, variety of algebras with binary operations. Then the derived variety is exactly the Manin-wide product of the initial operad and Novikov algebras, the operad corresponding to Novikov algebras. In order to get general derived variety, we have to consider Manin-wide product of the operad Var and GD dual differential Novikov-Poisson algebras, exactly. So, as we may see, the class of Novikov algebras and also differential Novikov-Poisson algebras or GD dual algebras, they play a crucial role in the computation of these derived identities. Well, there is, of course, another question of how can we calculate the identities themselves, because the definition of wide product is good, but it's not so constructive as, for example, the replication or splitting procedure. It is not hard to produce an algorithm how to calculate the defining identities of such a Manin-wide product. Say, suppose we have an operad corresponding to a variety of algebras with only one, for simplicity, one binary operation. So are Lie algebras, commutative, associative, Poisson algebras, and so on. We may determine left and right operations with a derivation and encode the operations left and right in the following way. This is exactly, this way corresponds to the construction of Hadamard product, exactly. The left product of x1, x2 is given by that tensor. The right product of x1, x2 is given by that tensor. The permutation of variables, as you may see, permute both variables in left and right factors. So, as soon as we encode left and right products, we may use compositions, the component substitution and renumeration composition I described before, in order to calculate all monomials of degree 3. All monomials of degree 3, those that contain x1, x2, x3, we have many monomials like that, they are all here. These expressions can be calculated just by compositions, operad compositions. And then we may span a linear space by these tensors and all permutations. The symmetric group S3 acts on these tensors, so we totally obtain 46 by head, so 48, right? 48 tensors. The corresponding space is denoted by M3, 2, the space of all monomials obtained by all permutations. And now, the spaces like Var3 or Nov3, they are homogeneous components of the free algebras in the variety Var and in the variety of Novikov algebras. We have canonical homomorphisms from the free algebra, free non-associative algebra, to the free Var algebra and to the free Novikov algebra. We may consider the homogeneous components of these homomorphisms. They are exactly the morphisms of operads, third components of that morphisms. And then, just by the definition of the wide product, they define these identities of the Manin wide product Var and Novikov. They are elements of the intersection of the kernel of tau tensor nu and intersection of the kernel with M32. So it's just from linear algebra. And in order to get the result, we have to calculate the intersection of two linear spaces. Of course, all these spaces, they are subspaces in M3 tensor M3, which is 144-dimensional. But the problem is standard, how to intersect two spaces. It can be done with a computer, for example. If we consider this intersection, then we would get the identities of the derived identities, actually. In order to get the same for general derived identities, the only thing to change is that instead of M3 tensor M3, we have this GD not from M3, it has two operations. So that will be M3 tensor M3 2, which is of higher dimension, but still this is a standard linear algebra problem. As soon as we intersect two spaces, we obtain the identities. And the calculation for example, associative algebras gives us the following result. The derived associative algebras are defined by two identities: central associativity, which is very expectable, and another identity. These two identities actually emerged in a paper by Lade in the following context. If we have an associative algebra with a derivation, then these two identities for these left and right multiplications, they hold on that the derivation algebra, differential algebra. We may say now that there are no other identities that hold on differential associative algebras, only these two. If we apply that procedure to Lie algebras, for example, then we obtain zero intersection. There are no identities for the derived Lie algebras. So d Lie, the variety d Lie, is equivalent to variety of non-associative algebras with one operation. One operation is just because, no identities apart from anti-commutativity. Left is equal to negative right. There are no other identities. And finally, I would like to discuss some unsolved questions. We have just proved that every identity that holds on dvar actually follows from Novikov times Var. In particular, the free algebra embeds, the free dvar algebra embeds into the free Var-Novikov algebra. But can we say the same for an arbitrary algebra? Can we can we prove a sort of embedding theorem for an arbitrary differential Var algebra? For commutative algebra, the answer was given by Bokut, Chen, and Zhang. I also know that the answer is positive for associative algebras. Every algebra satisfying these two identities can be actually embedded into differential associative algebra. For Lie algebras, the answer is also positive. But for Lie algebras, this result is a very easy exercise in Grobner-Chershov basis for Lie algebras. So to prove that every non-associative algebra may be embedded into a differential Lie algebra. And another interesting open question is related to the splitting procedure. In order to discuss a little bit more details, let us note that differential derived commutative algebras, they are exactly Novikov algebras. Splitted commutative algebras, they are Zinbiel algebras. Of course, good. So now we know that d var is now var white product with Novikov. Can we say the same for pre-var? It turns out that something is still true. Namely, if we consider an arbitrary algebra in a variety corresponding to the white product of Zinbiel and Var-algebras, every algebra in this variety would be actually a pre-Var algebra. If we have a morphism from here to some vector space, then this vector space would be actually a pre-Var algebra. In other terms, there is a morphism of operads from pre-Var to Zinbiel white Var. And in many cases, I've checked by straightforward computation with a computer. In many cases, this morphism is actually an isomorphism, but not always. For example, if we consider the variety of right nilpotent algebras with an identity like XYZ with brackets on the left is 0, the variety satisfying this identity, if we apply the dendriform splitting, we obtain less identities than in Zinbiel procedure. So the open question here is how to distinguish those good operads, like these ones, from those bad ones, like these ones. Good operads allow construction of splitting with white product. Bad operads do not allow. This is the last question of my talk, and it seems like I've finished. Thank you very much for your attention.
Okay, let us thank. Now, questions? Any questions? Comments?
No, I'm experiencing a problem with hearing you.
You can write your question if you cannot.
Yeah, if you use the chat window, that will be good.
Chat. Pavel, can you hear me?
Yes, I can hear you.
You, in the last statements, theorems, you didn't mention Jordan algebras. Can you say about this class of algebras, what related?
I haven't checked actually for Jordan algebras.
Okay. More questions? Well, let's see what's in the chat. No.
Excuse me, Professor.
Yeah, hi, Zeruy.
Yes, hi. When you construct var pre-var, and sometimes you make the left product as the same of right product, and sometimes you make it as sometimes you make a left product b equals a right product b, and sometimes make the inverse and the negative. And I don't know what is the rule of making this.
Well, the rule is very natural. Let me use the chat. Say, if a right b is d of a b. If the product is commutative, for example, then d of a b is just b times dA. If it was anti-commutative, then with negative sign. But b times d of a is b left a, right?
Yes.
So
what about Lie and Leibniz algebra?
Lie and Leibniz.
Right.
Yes, actually the same. In the case of for replication, this D is an operator of averaging operator. So in the case of Leibniz algebras, on one hand, we may consider A right B as Lie product of T. Now, let me use T B. But if the bracket is skew commutative, then it is equal to negative B times T of A. But the latter is nothing but negative B left A. If we use either of these two operations as a main one, say if we introduce AB, which is A right B, then this operation satisfies the identities of left Leibniz. If we use AB as A left B, then this is right Leibniz. If you fix either of them, you just obtain left or right Leibniz algebras. This is the whole difference.
Okay, thank you very much. Thank you.
You're very welcome.
And Pavel, for Jordan algebras, probably it's difficult because it's of degree 4, because all these exams...
yes, the operad is non-quadratic, that's true. But the Y product can still be defined, and the dendriform splitting can also be calculated. Moreover, it is already calculated by Chen-Min Bai and co-authors, so-called pre-Jordan algebras. The splitting is a very algorithmic procedure, and calculation of the white product is also algorithmic. But the dimension is, of course, higher, because in dimension 4, the embedding space, the enveloping space for solving the linear algebra problem has much higher dimension, of course.
Thank you. All more questions? Any more questions, comments? Okay, if there are no more questions, let us thank Pavel again.
Thank you so much for watching.
Okay, and so it's all for today. It was the most, we were very far to the east today, to Japan, Novosibirsk. Well, and the next Thursday, well, I had to check. Lucia, can you say what we have the next Thursday? He's not here. Let me see. So what we have. Well, I cannot see.
It's Patrick Lemer.
Okay. Thank you, Lucia. So it will be at standard time at 2 and 14 in Brazilian time. Yes, it's standard time. So see all of you.
See you.
The next Thursday. It will be Patrick Lemer at 14 in Brazilian time. Bye-bye, everybody.
Bye.
Thank you, everybody. Thank you, Pavel, again.
Thank you.
Very nice talk.